Hello, and welcome to the video accompanying Chapter 9 on the topic of gravity. This chapter covers the topic of gravity and is in Physics 12th edition by Hewitt. Okay, so we have a few subtopics to cover in this lecture. We're going to talk about something called the Newtonian synthesis, so the early history of discovering the law of gravity, also known as the universal law of gravity. Then we're going to talk about a fitting constant in the gravitational formula, which is called the universal gravitational constant. Essentially, I call it a fitting constant because it is an experimental value that makes the equation work. That's pretty great, right? And then we'll talk about the inverse square law, which is one of the key mathematical features of the universal law of gravity. Then we'll get into weight and weightlessness, how it relates to things like orbit, for example, being in a space station. Then we'll get into some specific consequences of gravity in our lives here on Earth, such as the ocean tides. Then we discuss some more kind of far out ideas that we'll kind of circle back to in the very last chapters of this book, such as gravitational fields, Einstein's theory of gravitation, black holes, and universal gravitation. But we won't spend a lot of time on those final topics. Okay? So, what is the Newtonian synthesis? So Newton was not the first to discover gravity. Newton discovered that gravity is universal. Okay? Other people had observed gravity. In fact, one generation before Newton, Galileo had found that gravitational acceleration was the same for all objects here on Earth. But Newton made the step of saying, okay, well, if gravitational acceleration is the same for all objects here on Earth, maybe gravitational acceleration is not itself, not the value of acceleration being constant, but maybe the cause of that acceleration, the explanation, the force behind that acceleration, maybe that is truly universal. So the same type of force that creates constant acceleration here on the surface of Earth, which we know to be 9.8 meters per second squared, maybe that same cause creates the gravitational acceleration experienced by the moon towards Earth, which is much smaller. Okay, so it is a legend that Newton sitting under a tree was inspired. Okay, so a little bit of ancient history. In Aristotle's time, motion of planets and stars was natural, not governed by the same laws as objects on Earth. Okay, so it was a separate thing. The heavens were governed by separate physics. That is not the case. Okay, since Newton, for the last 500 years, we have built a huge body of evidence on the idea that the same laws that apply here on Earth apply to space. The same physics that causes planets to orbit the sun causes balls to roll down ramps on Earth. Okay? So, but that was not known in Aristotle's time over 2,000 years ago. Newton, in the 1500s, recognized that a force directed towards the sun must act on planets. This is similar to the force that Earth exerts on an apple that falls towards it. See, that's the idea of universal. The same type of force that pulls Earth towards the sun pulls an apple towards the surface of Earth. All right? And you might say to yourself, wait, why do we keep talking about the moon being pulled towards Earth and the Earth being pulled towards the sun? That's not right. We're circling those things. Well, no, we're falling towards the sun and the moon is falling towards us. It just so happens that we're moving really fast, so we never hit the sun and the moon never hits Earth, but we are absolutely being pulled and the moon is being pulled. Okay? More on that later. Newtonian synthesis states that the same set of laws apply to both celestial, that's like planets and moons and stuff, stars, and terrestrial objects. So everything terrestrial just is everything on Earth. All right? So the law of universal gravitation states that everything pulls on everything else. Okay, so it's truly a universal law. All right, objects in the room that you're sitting in while watching this video or listening to this video are being gravitationally pulled towards you. You exert a gravitational attraction on them. Okay, it is very small, but you do. Okay, every bit of matter is attracted to every other bit of matter. It turns out that we don't notice the gravitational pull between objects because the gravitational pull between all those objects and the Earth is much, much greater. Okay. Every body attracts every other body with a force that is directly proportional, okay, directly proportional to the product of their masses. So see, we're getting to the technical side of here, and inversely proportional to the square of the distance separating them. So that sentence is a bit of a mouthful. Okay, we're going to see it in the equation form, but it looks like this. So force of gravity, so G subscript for gravity, is then some constant. We'll talk about that. That's that fitting constant, the constant that makes things work. and then the product of the masses, so 1 and 2, mass 1 times mass 2, multiplication symbol between them. And then, that's the direct part, because they're in the numerator. And then, when we're talking about an inverse proportionality, well, inverse proportionality is just code for put in the denominator. And we're told it's the square of the distance. Oh, so then it's r squared. That right there is the universal law of gravity. All right, let's continue with it. Okay, there it is. All right, m is the mass of the object, and d is the distance between their centers. Okay, so m1 and m2, m1 could be the Earth, m2 could be the moon. m1 could be the Earth, and m2 could be a person, right? So it's just any two objects. m1 could be the Earth, m2 could be a satellite, right? And the d is the distance between their centers, okay? So d wouldn't be, say, the distance from the surface of Earth to the satellite, if m2 is a satellite. It'd be the distance from the center of Earth to the satellite. That's been crucially important, all right? So the greater the masses, m1 and m2, of the two bodies, the greater force of attraction between them, okay? So, right, so this proportionality says that if you want a large force, you want a lot of mass. Okay? The greater the distance between two bodies, the weaker the force. And in fact, since the distance is squared in the denominator, it falls off rather quickly, right? You double the distance and you cut the force by a quarter. All right? So Newton's most celebrated synthesis was and is of, so what did he do? What did he synthesize? Synthesize means bring ideas together. He brought the earthly and heavenly laws together. Okay? So, what's G? Okay, the universal gravitational constant. So gravity is the weakest of the 4 known fundamental forces. We'll talk about the other 3 of the fundamental forces later. So far, this is our first one. Okay, so on your checklist of fundamental forces, this is the first one. And the whole idea of fundamental forces is pretty amazing. It's the idea that every movement in the universe can be explained by a force that's created by one of the 4 fundamental forces. It's a totally comprehensive understanding of motion of the universe. Okay? Now, gravity is a really important one. It causes amazing things, the creation of stars, black holes, which we'll touch on, but it is by far the weakest. Okay? So the actual form of the equation, because notice on the previous page, 2 pages, excuse me, this is not an equation. This little symbol means proportional. That means that the units on both sides of that symbol need not match. But as we get over here, now we have an equation. The equation means that we have to have the same units. So on the left-hand side, we must have newtons because force is measured in newtons. Thus, the units on the right-hand side must also be newtons. So that means this constant here, big G, serves the job of making sure the units work, but also makes it numerically work, okay? And the value of the universal gravitational constant is 6.67 times 10 to the negative 11, and it's Newton square meters over square kilograms, all right? Now, 10 to the negative 11, that means it's a really small number. In fact, that means that it's 66.7 trillionths of a Newton square meter per square kilogram, right? So very, very, very small. Why so small? Because, as I said, gravity is a very weak force. Okay, how do we even know this number? We actually only know it through experimentation. There's no law that tells us this number. We observe how quickly things accelerate towards each other, and we calculate this number. Okay, so the accuracy of this number is dependent on the accuracy of the experiment that has calculated it. It is entirely an empirical value. All right, now is there some explanation for why it exists? Is there something about the universe, about the Big Bang, about the very nature of space and time that determines this number? Probably, but we don't know that yet. Okay, that's the forefront of modern physics right there. So once the value was known, the mass of Earth was calculated as 6 times 10 to the 24 kilograms. And actually we know it to be more accurate, 5.997 times 10 to the 24 kilograms, okay? So that's pretty amazing. Once we know the gravitational constant, we can calculate something that otherwise we couldn't find out. How are you going to measure the mass of Earth? You can't put Earth on a scale, okay? But if you can find this constant independent of the mass of Earth, which there are experiments that do that, we won't get into it, then we can determine the mass of Earth. Once we know the mass of Earth, then we can do that. Then we can find the mass of the Sun, and so on, right? So it opens up all these unknown values and makes them known. So the universal gravitation constant G, which links force to mass and distance, is similar to the familiar constant what? What similar empirical constant exists that's like the gravitational constant uppercase G? Pi, of course, because pi is a ratio of the circumference of a circle to its diameter. right? We don't know why it's 3.14. We just know it is. And we can measure it as accurately as possible, right? See? Kind of amazing, right? The mysteries of the universe. Okay, so what is an inverse square law? Okay, so this is something we'll talk about later when we talk about Coulomb's law. So that's a good one to tuck away in the back of your brain. Coulomb's law. Okay, that's a later chapter. Okay, well, don't worry about it. It'll be a while till we get there. But it turns out that there's other laws in physics that obey the inverse square relationship. So we kind of collectively call them the inverse square laws. Okay, so what is it? So it relates the intensity of an effect to the inverse square of the distance from the cause. Okay, so in the equation form, it's in that it basically comes out as intensity equals 1 over distance squared. Why are we bringing it up? Well, because the universal law of gravity follows the inverse square law, right? It has a distance squared in the denominator. Okay, so for increases in distance, there are decreases in force. Even at greater distances, the force approaches but never reaches zero. Because if you make r really, really big, right, like millions of kilometers, then Fg is going to be infinitesimally small, but never truly zero, right? Because there's no way to divide by a value and get zero, okay? It just approaches zero. That's kind of the mathematical term for it, right? Okay, so where does this idea come from? Well, we can kind of think about it as maybe spraying paint or sound spreading out, because there's actually a very intuitive explanation for why certain things, including the gravitational force, must follow an inverse square law relationship. Let's look at a picture, okay? So let's think about paint, right? If I spray paint on a wall and I have a distance of 1 unit, right there, 1 unit distance, then I'm going to get a very thick amount of paint, right? In fact, that paint's probably going to run, right? Because it's too thick, all right? So I'll get a 1 layer thick area that is 1 area unit, okay? What if I step back and I double my distance? So now I'm 2 units. Notice we're not using any official meters or anything. We're just, this is general. 2 units of distance away. Well, think about the spray. The spray spreads out, right? So if I double my distance, that means now the spray is not going to cover double the area that it did before, but 4 times the area. If the spray is covering 4 times the area, but it's still the same can of paint, that's the same amount of paint, that means that the thickness of the layer will be 1/4 as thick. The intensity of the paint has gone down to 1/4 by doubling the distance. What if I triple the distance? Well, now the area is 9 times as big as it was when the distance is 1. Thus, the thickness is 1/9. What if I quadruple the distance? Well, now the area is 16 times bigger. Thus, the thickness of the paint on any given segment of this much larger area will be 1/16 as thick. That's the inverse square law, okay? And it's exactly what you would expect from spray paint. And it applies to sound, it applies to earthquake energy, it applies to gravity, okay? So the inverse square law, in effect, looks like this. If you consider an apple that weighs 1 Newton on the surface of the earth, right at this point, if I double the distance and I measure the weight of an apple that is 1 earth diameter, 1 earth radius above the surface. So now maybe, you know, I'm up on some ridiculously, unimaginably tall tower that is one earth radius above the surface. Well, if I was to measure the weight of the apple there, it would weigh 1/4 as much, all right? If I was to go a distance away from the apple, all right, or a distance away from the surface of Earth that is 4 times greater than d, now the apple would weigh 1/16 as much. So as you move away from Earth, the gravitational pull of Earth falls off. So essentially, if I go off into space, some 5 times the radius of Earth, which would be about 30,000 kilometers off into space, and I just go up there and I just kind of stop moving, I'm just at rest, just floating around. Earth is still going to pull on me, but it's going to pull on me with 1/25 as much force, which means my acceleration would be 1/25 as much as the acceleration on the surface. So instead of falling towards Earth at almost 10 meters per second squared, I'm going to fall to Earth at less than 1 meter per second squared. So I would start accelerating to Earth because there really wouldn't be much else to pull on me, but much, much slower. Okay? But as I got closer, the force would start ramping up again. So by the time I got to the surface, I'd be falling at the maximum acceleration. But of course, I would have burned up at that point because you'd pass through the atmosphere at high speed, a lot of friction. All right? So the force of gravity between two planets depends on what? Okay, make sure you can answer this. Pause if you need to. Masses and distance. It's right there in the formula. Okay. Now you might be like, oh, wait, it depends on big G too, right? No, big G is just a constant. Okay, it's just the numbers. Just always 6.67 times 10 to the negative 11. Okay. If the masses of two planets are each somehow doubled, the force of gravity between them does what? Imagine two planets. They both have, some mass, M1 and M2. And then we just, all of a sudden, magically, they become 2M1 and 2M2. Now the force of gravity between them is quadrupled. Why? Well, look at the formula, right? Because before, initially, I'll call it 0 for initial, I have G M1 M2 over R squared. Okay, well now, the new one, I have G 2M1 2M2 over R squared. Okay, well then I can then take the 2 by 2, factor it out to the front, and I get 4 G M1 M2 over R squared. Oh, well this whole business here is just FG with 0, which we call FG naught. Well, sure enough, the force has gone up by a factor of 4. Okay? If the masses of one planet, or if the mass of one planet is somehow doubled, the force of gravity between it and the neighboring planet does what? Okay, so now we're only changing the mass of one planet. I'm doubling one of them but leaving the other one the same. Well, in that case, what's going to happen? Yeah, just doubles. Okay? So, what about weight and weightlessness? Okay, so weight, what's the definition? Well, we talked about this a bit when we introduced Newton's third law and, and then some other early chapters on force. But weight, the force an object exerts against a supporting force. Okay, so weight and the normal force are force pairs. Okay, all right. So standing on a scale in an elevator, accelerating downwards, less compression in the scale means weight is less. Okay, so your weight can be reduced if you're in a downward accelerating reference frame, like an elevator that's speeding up on its way down. By the way, if the elevator is moving down at constant velocity, then there's actually no change, right? Constant speed. There's no change in your weight. It has to be accelerating. What if you're standing on a scale in an elevator that's accelerating upward? Well, that's like an elevator when it first starts moving up. You feel momentarily heavier. Your weight has actually increased. If you're standing on a scale, the digital readout of that scale would jump up a little bit higher before it leveled off when the elevator hit constant speed. If it has a chance to hit constant speed. Some elevators are, if they're only going up a couple floors, accelerate basically up, then start accelerating down right away, right? Because they kind of speed up and then they almost immediately have to start slowing down, okay? So you go from feeling a little bit heavier to feeling a little bit lighter, and then the ride is done. All right? But the point is that having vertical accelerations, like in an elevator, a good real-life example of it, do change your weight. Okay? What about weightlessness? Well, weightlessness is like free fall. No support force at all. Right? This guy right here is weightless. He'd just be floating around in the car until him and the car hit the bottom of the cliff below. Well, astronauts are also weightless. All right? Astronauts in orbit are without support force and are in a continual state of weightlessness. All right? So that's because they are in free fall. Right? Weight and weightlessness. All right? So here's an example. Normal weight when the elevator is at rest. Greater than normal weight when the elevator is accelerating upward. Less than normal weight when the elevator is accelerating downwards. Zero weight when there's catastrophic mechanical failure and the elevator is in free fall. All right? So when an elevator accelerates upward, your weight reading on the scale is, make sure you can answer this, greater. All right? You're being pushed into the floor more. When an elevator accelerates downwards, your weight reading is, you know it, less. When an elevator cable breaks, the elevator falls freely, so your weight reading is, that's right, 0. Right? Not a good situation. So if you weigh yourself in an elevator, you'll weigh more when the elevator, this is just phrased differently, I want to make sure you understand this. Okay, when are you going to weigh more? All right. Well, it's not A or B. It has to be accelerating. Movement is not enough. Okay, because movement can mean constant velocity. The elevator has to be accelerating. And specifically to weigh more, it has to be accelerating upward. All right. Okay, ocean tides. All right, so the difference between ocean levels at different times of the day are called tides. There are typically 2 high tides and 2 low tides every day, not 1. Okay, so why is that? Well, ocean tides are caused due to the gravitational attraction of the moon. Unequal tugs on Earth's ocean causes a stretching effect that produces a pair of ocean bulges because the 2 bulges on opposite sides, high tide, occur every 12 hours. All right? So the idea here is that the water here is getting pulled towards the moon. The water here is also getting pulled towards the moon. All right? That creates a bulge on both sides that are in line with the moon. On these sides, the side that's kind of facing out to you, if you imagine this, that the Earth here is a 3D object, and the side that's behind, right, so on the back side, those two sides don't have a bulge. Those are the low tides. This bulge makes sense because that's the side of the water that is being pulled towards the moon. You can think of this secondary bulge on the far side as the case where the water is lagging behind because it is getting pulled the least by the moon. Okay? So during the new moon or full moon, the effects of moon and sun add up, causing most pronounced spring tides. Okay, so we call these spring tides not because they happen to happen in the months of spring, that's just the term they're given, but they happen every new moon and full moon because the sun does contribute to the tides. It may be much, much further away from us from the moon, but it is also much, much more massive. And although its contribution to tides is not as great as the moon, it is significant. All right? So here we have the combined effects of the moon and the sun. When the moon is halfway between a new and full moon, which is a quarter moon, all right, so this is right here, this could be like a first quarter and a third quarter moon. All right, so during those phases of the moon, when half the moon is illuminated, then you have what is called a neap tide. These are weaker tides. There's still 2 high tides a day and 2 low tides a day, but they're not as dramatic. Okay, so gravitational fields. The interaction between Earth and the moon is action at a distance. Okay, that was kind of the term that Newton gave it. That's a term we still use today. How do they interact without touching? So how is that, right? How does gravity even work, right? I mean, the force of gravity pulls on the moon, from Earth. Somehow there's a gravitational attraction between the moon and the sun. I mean, what's happening? There's not like there's some line connecting the two. It's not like a tension force. So how is it? How does gravitational force actually work? Well, one way to think of this is Earth is surrounded by a gravitational field, an imaginary force field. The moon interacts with this gravitational field. The gravitational field is an alteration of space around Earth. Okay, so it is an effect to space itself, not visible to the naked eye, but it is an actual change to space. The gravitational field is an example of a force field. Another example is the magnetic field or the electrostatic field or the nuclear force field. These are examples of fields. They just exist in space. So fields are represented by field lines radiating into the Earth. They radiate into the Earth because that's the direction of the force, because the force is attractive, okay? The inward direction, okay, indicates that the force is attractive, as I said. The crowding of arrows closer to the Earth indicates that the magnitude of the force is larger closer to the Earth. So the spacing is kind of the same way you'd read the spacing on a topographic map. The closer the lines are, the steeper the slope on a map. Here, the closer the field lines, the stronger the force. So it's telling us that as we get close to the surface, the force gets stronger. Well, that's completely consistent with the inverse square law, isn't it? With the idea that we elaborated on with the analogy to a spray can. Inside a planet, the force decreases to 0 at the center. Because the pull of mass of Earth below you is partly balanced by what's above you, the fall off is no longer an inverse square law, but just an inverse law. So the force of gravity inside the Earth falls off linearly, so it falls off as 1 to the r, whereas outside the Earth, it falls off as 1 to the r squared. Okay? And that's because some of the mass above you is canceling with mass that's over on the other side. Okay? So the overall effect, which you can prove with calculus, is a linear relationship inside a solid spherical object like the Earth, and is linear or inversely linear, and outside it's an inverse square relationship. Okay? Okay? So, by the way, if the Earth was not solid, if it was a hollow sphere, as soon as you went inside it, the gravity would completely cancel out and you'd be weightless. So if you imagine some sci-fi giant planet that's just a shell, as soon as you were to break through that shell, you would be weightless. So the entire empty interior of the planet would be weightless. It's also why the idea of a lost world, the idea that, if there's some other, kind of lost world of dinosaurs or something that lives on the interior inside planet of our planet wouldn't work, because again, it would have to be weightless. You couldn't have gravity on that inside side of the shell. You could still have gravity on the outside of the shell, but inside you'd be weightless because all the effects would cancel out. The mass on one side would completely cancel with the mass of the shell on the other side, okay? But in the case of a solid object, the cancellation only applies to the mass that's above you. So let's say that you're at that depth. All the mass that's interior still pulls you inwards. That's why you would still feel weight, but it would be decreasing. All right? Well, let's continue on the example of a solid planet like ours. What if you dug a hole through it, right? So another kind of fanciful thing to think about. So suppose you dig a hole through the Earth to the other side and jump through it. And somehow you've reinforced your hole so it goes all the way through the core of the Earth, through the molten core of the Earth, but doesn't melt, doesn't get destroyed. It's a stable hole, all right? Well, as you fall, your acceleration toward the center will go down because, as you can see, the gravitational field strength goes down as you move towards the center. That means your force goes down, so that means your acceleration will decrease. So at first, your acceleration will be gravity. Once you've fallen halfway down towards the center, your acceleration will be half of gravity. Once you reach the center, your acceleration is zero. Does that mean that you would just come to stop at the center? No, having an acceleration of zero doesn't mean your velocity is zero. That just means that at this point right here, you'd be momentarily moving at a constant velocity. But look what happens next. As you pass through the center, your acceleration starts to ramp back up. But what way is it facing? Well, before the gravitational acceleration was facing down because it's towards the center. Once you pass through the center at a momentary constant velocity, then the acceleration starts to face back the other way because it always faces towards the center, which in this picture now starts to face up. Well, that means that what's going to happen, you're going to pass through the center at constant velocity, and then you're going to start decelerating. At first, you're going to be decelerating a little. By the time you get to the surface on the other side, you're going to be decelerating a lot. In fact, you're going to momentarily come to rest over here, just like you started at rest. And what's going to happen? You're just going to oscillate back and forth forever. Assuming there's no air resistance. So if you somehow evacuated this tube and just turned it into a big giant vacuum tube, then you would just have a huge oscillator and you would just go boing, 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 boing. But each fall would take many minutes. Okay? Pretty remarkable. All right. So now Einstein's theory of gravitation. The gravitational field is a warping of space-time by a planet. Okay, so this is continuing on the what is the field truly? Okay, well, Einstein understood in a way that had not been understood before. We're talking about the early 20th century, the early 1900s. And he said, okay, well, space-time itself is getting sort of bent by the idea of concentrated mass like a planet or a star, all right? Just as a massive ball would make a dent on the surface of a waterbed, all right? Or imagine a sheet that's being held taut and you drop a heavy ball on it and it kind of stretches, it makes a indentation, right? Looking something like this. The warped space-time affects the motion of other objects, just as a marble rolling on the waterbed gravitates towards the dent, right? It's an accelerated. If I even give it some sideways velocity, it's going to kind of take a spiral path, right? Okay? So, when a star shrinks, all of its mass is now concentrated in a smaller radius. So the gravitational force on the surface increases. When D increases, F increases, all right? So you imagine a indestructible person standing on a shrinking star. As the star shrinks to 1/2 its radius, their weight went from 10,000 newtons to 40,000 newtons. Why? Well, because it's proportional to the radius squared. So cutting the radius in half quadruples the force. All right? So that means the gravitational force is getting stronger and stronger and stronger. Well, it turns out that stars can shrink to an unbelievable tiny fraction of their original volume. When stars collapse, they leave their cores behind, which have most of the mass that they had when the star was huge, but in much less space. For example, a white dwarf, which is the ultimate fate of a star like our sun, is the size of Earth, but will have most of the mass that our sun currently has. That means that a white dwarf is a huge gravitational force. But there's more dramatic examples. There's things called neutron stars that are the size of cities that have all the mass of a star. So we're talking about a city that has a mass that's 100,000 times greater than the mass of Earth, all concentrated in one place. But there's even a more extreme example, and that is a black hole, where you have something that is just the size of, instead of a city, a park that has the mass of something like our sun. All right? So when the star becomes so small and the gravitational force on the surface becomes so large that even light cannot escape the surface, anything in its vicinity will be attracted to this warped space-time and lost forever. Okay? So what do we mean by it? Well, on the one hand, a black hole is just a really, really highly concentrated bit of matter. So it has this idea that it has a radius that is just, maybe the size of a college campus or a city park. But on the other hand, it's a little bit more far out than that because it is so massive and its gravitational force is so great that now the escape velocity is greater than the speed of light. Well, the speed of light is the fastest thing in the universe. So if nothing can escape a black hole, what is it truly? And furthermore, the size is more of the perimeter because we don't really know what's going on inside because there is nothing to stop it from collapsing. So does the matter just continue to collapse to a single point known as a singularity? Maybe. All we know is that there is some perimeter upon which light cannot escape. But since light is also information, and information travels as light, then that means that nothing can come out. We can gain no information about the black hole. It is a mystery hole. So we don't know what the singularity is because the perimeter, the event horizon, the edge of that black hole is the edge of knowledge. All right? So what would happen to Earth if the sun became a black hole? Well, not much. We'd still have the same, we'd still be able to orbit it. But of course, we also wouldn't have any light, so the planet would just freeze over into an ice ball. But it wouldn't affect our orbit. The only time that a black hole is able to eat things, like they talk about in sci-fi movies, is if an object is close enough that it experiences tidal forces. So if Earth became a black hole, then the moon would be in trouble because the tidal forces would cause the moon to eventually collapse and then spiral into the black hole. But you have to be close enough to have significant tidal forces from that object. And you might say, oh, well, but didn't we just say that the sun exerts tidal forces on Earth? But they're quite small. And so it wouldn't significantly affect our orbit. We would just continue to orbit the black hole, but get no life-giving light from it. All right? A wormhole is a theoretical idea that since a black hole is essentially a hole in space-time, that maybe that hole has to connect somewhere and it comes out in another space-time or another section of our own space-time. All right, so finally, the idea of universal gravitation. Everything attracts everything else. Earth is round because of gravitation. All parts of Earth have been pulled in, making the surface equidistant. The universe is expanding and accelerating outwards. All right? Okay, so we'll end it there. Some big ideas. Our first of our 4 fundamental forces discussed here, and we'll have a chance to talk more about satellites and orbits in our chapter on projectile motion, so look forward to that. But this is our second lecture for this week, and hopefully it was an interesting one. Thank you so much for watching this video, and send me any questions about the content that you may have.